for the patience. So I'm Serena Brizio. I'm from Thales Alenia Space, and we did this project jointly with Lorenzo Guarino, who is now my colleague. At the time, I was the intern in Thales Alenia Space, and he did his master thesis on this topic. And the project was led jointly with Mathworks, especially with Marco Bimbi and Stephan van Beek, the Mathworks application engineering. And the goal was to enable MBSE with the simulation for this pre-phase A ESA project called Solaris. Okay, so this is the agenda. First of all, I'm going to show to you some information about Solaris, this project, pre-phase A project from ESA. Then I will explain to you why we have used an MBSE approach specifically for this study. Then what were the challenge and the needs, especially from the customer. And we will show to you, I will leave the floor to Marco and Lorenzo to explain to you better the solution that we have put in place in terms of the process and the methodology that we have followed. This bridge between the static world of Capella and the simulation environment of System Composer and all the analysis workflow. Then I will give to you the outcomes, especially from Thales Alenia Space point of view, and Marco will give to you his outcomes on Mathworks point of view, and we will leave also the time for the Q&A. So first of all, what is Solaris about? Solaris was a space-based solar power project with the aim to collect on orbit the sunlight through huge solar panels, transform the solar energy into electrical power, then again on orbit, convert it again into radio frequency, send this radio frequency to Hertz, and on Earth have these antennas called rectifying antenna, able to capture this beam, convert it again into electrical power, and distribute and transmit and distribute to the end user. This was a consortium led by Thales Alenia Space Italy in Turin, with the participation of Thales Alenia Space France, who helped us to define better the antennas on ground and the rectifying antenna, the antenna in orbit and the antenna on ground, and the electric energy provider in Italy, which is Enel. Enel helped us to the construction of the network of distribution of the electric power. So why we have used MBSE in this project? First of all, because it was a deliverable asked by ESA. So we have to provide the architecture in form of a digital model. And then we have applied the whole methodology Arcadia since the beginning, so since the beginning of the project until the choose of the final solution. So we passed through the definition of different trade-off analysis, different technologies that we have taken into account, and with all the interconnection among these technologies, these functions that we have settled. And it was extremely helpful to define in a designer point of view the overall architecture. But then if you click Marco, we realize that it wasn't enough, because we have to optimize this architecture with the harmonization of these different technologies in order to find the best compromise. And we have also the needs to analyze the different data coming from the choosing of the optimal orbit, the choosing of the different technology of the cells, the location of the ground antenna, the location of the inclination of the orbit, so different kind of analysis. And so we need to match these two words, the design world and the simulation world. Because this was the challenge, to match the technical viewpoint with all these multiple actors who were acting in this project, and also the economic scenarios, because we had to find the best compromise in terms of cost and in terms of mass to carry on space. So here the needs to match the static viewpoint of Capella into the dynamic viewpoint of System Composer. So it was in this framework that Mathworks came to Thales Alenia Space to present their tool, fully implemented into the Simulink environment called System Composer. And here the idea to match for this purpose the two environment, the Capella and the System Composer. So now I will leave the floor to Marco Bimbi to explain to you how we match these two data models in order to be able to perform analysis into the System Composer. So please, Marco.
Thank you, Serena. So just a quick overview on first what the process and the methodology that was used here is. So you see here many things in this slide, but essentially on the left-hand side, you see the high-level requirements. So those are, let's say, the constraints or the wishes that the Solaris project has to fulfill, whether we're talking about cost, total mass, amount of energy that you put on the networks, etc., and the different constraints that you might have while designing this system of system as it is. On the top, you see essentially the Capella methodology, which I'm not going to spend time on it. It's known to everyone here, I guess, that Serena was mentioning before. And on the below part, you see how we try from Mathworks perspective to connect those two words. So essentially the idea was like, okay, let's do all the typical layers that you do in Capella up until the logical architecture, where you have defined your architecture from logical point of view. And then let's import this in our environment, specifically in what is our tool for model-based system engineering ecosystem composer, to then instrument, let's say, this model so they can simulate and run trade-off analysis. Now, for completeness, we did also import the physical architecture, the functional architecture, and did maintain the traceability between the two, or the allocation between the two. But what we used to instrument and enable the simulation was the logical architecture. So what we did import the logical architecture from Capella into the System Composer, and then we transformed that into what it's called product architecture. Think about as a product architecture as a sort of a physical architecture, and I put it in quote. It's not the same physical architecture that you might do here, but it's essentially how you regroup the logical component into system. All those logical components belong to the ground station, those belong to the satellites, those belong to the network grid. And then we started instrumenting those product architecture, and as you will see later on when Lorenzo will describe the analysis workflow, we did this in two steps. The first was essentially just attaching metadata to the product architecture for doing a preliminary designing optimization, obviously against the requirements. So the data that we attach it to it, that you know as stereotypes and properties, were there to enable a very fast analysis just using MATLAB scripts to run some trade-off analysis. For example, where is best to place the ground station? What should be the optimized area of the solar panel or the antenna, and so on and so forth. Later on, with this information as a restriction of the design space that you could have, we then implemented for each of the logical component a simulation model. We did this in Simulink. You could do this in different ways, but essentially the idea of that is to perform a high fidelity simulation model and calculate things like return on investment, total mass, what's actually the total energy that you're going to get in the grid, taking into account the various losses that you might have in the different transfer of energy between the different systems. And I think, as you will see later on, this framework has been built so that at any point in time where you are in the analysis, you could go back and do, for example, another low fidelity preliminary optimization and go back and forth. Because as you all know, this is an iterative process and it's not a waterfall. So how that look like? Something of like that. On the left-hand side, you see the Capella model specifically for the satellite and the ground station. And on the right-hand side, you see the converted model of the logical architecture, and then the grouped one into the product architecture, which essentially is the composition of the different systems that they are interacting amongst themselves. And there, in the product architecture, is where we are going to run the low-level fidelity analysis and the high levels, all the design optimization. So up until now, I said multiple times that we have import the model from Capella into System Composer. So how does this import works? Not magic. It's essentially knowing what you're looking for and knowing how you want it to translate. So this is the generic way of how this import would work. So here on the left-hand side, you essentially see the XML file that you can get from Capella. We are able to parse this XML file, knowing what we are looking for, and then we can translate this into a different set of artifacts. So not only System Composer, if you would have requirements, if you would have interfaces, etc., this will become different artifacts in the Mathworks environment. This post-processing is what I just said, when you just then instrument the model with the stereotypes and metadata that you needed. Now, how do you get from here to here? Well, you need to know what you want to translate. So you need to know what you're looking for in the XML file, and you need to know how you want it to translate in our environment. So here is where this customization comes in. What this customization does, it tells the script, search for this element in Capella, for example, a logical component, and translate it into a component in System Composer. Or search a data type in Capella and translate this into an interface type in our Mathworks environment. This is the translation rule that we use specifically in this project. What I wanted to stress is this is basically a sort of a configuration file that you give to the tool. That's why it's called customization. What this is about is essentially a JSON file where on the left-hand side here, you map the tag of the specific element that you're looking in Capella in the XML file, and you map with the specific keywords, which is essentially the tag corresponding to the element that you wanted to translate it in our meta model. And then all of this does is essentially a pipeline that looks for those tags in the XML and creates the corresponding element into System Composer. And so this is completely, obviously, customizable, to the point that in this project, we didn't import requirement and there were no profile, ad hoc profile and stereotype in here. But if you wanted to, you could also do that by extending this customization to say, okay, now also look for profile and translate them into profiles and so on and so forth. There is a link to an article that was written quite some time ago on how this works, and there are more details on how you could do that. So just leaving it there as a reference for you. So now you might ask a question. Okay, you're telling us that the model is done in Capella. You are importing and you are augmenting the model for analysis purpose. But that means that the source of truth for the architecture lives in Capella. So what happens if during the simulation or for whatever reason, the Capella model has to change? Do you have to do all of this manually again? Because this works nicely, and you could see how that might work for a first import when everything gets created for the first time. But I haven't said anything about diff and merge. Well, we kind of had this problem, obviously, because you have to do many modification. And so what we did is something like this. So we didn't actually have any diff and merge into the import as such. We then leverage the diff and merge that is in our product to create the new updated model. Reason why we did that, it's simply convenient. You could do a diff and merge in the importer if you wanted to, but as we have a graphical diff and merge capability, and we can actually auto merge things if there are no conflict, we prefer it to offload it to our environment. And so the way it works is like, consider V1 as the first import and V2 is import number 2. So you get in V1 your Capella model, you're using the bridge to transform this into System Composer, and you do your modification, which means you are regrouping the component together, and then you are adding the stereotypes, and later on, as you will see, the implementation. And this keeps you to this V1 modification. Now someone comes along and modifies the Capella model, again, for whatever reason, either from the analysis or because there is a new requirement coming from the stakeholders. So you have your version 2. What you could do at the moment is you can import the version 2. And this, if you would use any config control, say, for example, Git, this would be your development branch. Let's assume the master branch is only the final modification. So you're on the development branch, and this is another branch. What you can do, you can actually compare those two, and you are comparing, in this simple case, just a model. but you could compare all the other artifacts and essentially understand what the differences are and then merge them together through the graphical merger view. And what this would give you is version 2 plus modification, which becomes your new source of truth on which you're going to perform all the analysis that Lorenzo is going to talk about in a minute. And then obviously, if you would have a version 3, you simply repeat this process all along to create a new source. So that's basically the way we ingested the information and we handle the potential update to create really a digital continuity between the two. Now I'm just gonna leave the floor to Lorenzo to explain the analysis part.
So my colleagues talked about the first two blocks of this analysis workflow that you see here. So the creation of the architecture and the population of the metadata. Now we are going to more detail on the type of analysis that the framework permitted to do on our side, on TAS side. So the type of analysis were divided in two. One what is called low fidelity analysis, as already Marco said, and the other the high fidelity analysis. The low fidelity analysis has the objective to have an optimization of the three main areas of the system. So the solar panels area, the antenna on board area, and the ground power station on ground area. This is done by an optimization code than in MATLAB. And in the framework, you can change the different weight optimization of these three main areas, but also other inputs like, for example, frequency or other variables. So at the end, you pick one of the solutions that you have run. You update the architecture metadata with these inputs. So you have saved the work you have done, and you can pass to the high fidelity analysis. So the architecture metadata now serves as an input for the subsequent analysis, because now you want to make other design choices, but in this case mainly for what concerns the mass or other technologies that impacts the cost of the final architecture, but also the scenario that you want to simulate. So for example, you want to simulate a nominal day of power distribution, or a worst case scenario for the eclipse in orbit, and you can see how well the parameter costs are at the end, or the mass cost, the number of launches. So if you are okay with the results you obtain, you end the workflow like that. But you can restart if you are not okay, for example, with the parameter, the energy return on energy investment with that solution. You can restart from the scratch, so from the low fidelity analysis, doing another optimization to obtain a different combination of the three areas, and then retry with the high fidelity to see what is the new architecture with power simulations and the other parameters, which are very important at the end. So going more into detail to the low fidelity analysis. As I already said, the objective was to find an optimal combination of the photovoltaic area, the antenna area, and the ground power station area. This was done with an objective function in our optimization code, where the objective was the sum of these three areas with three weight factor, which could be selected by the user. So the user can give more importance to, for example, optimizing the antenna area and the solar panels area with respect to the ground power station area, but also other different choices. And the other design variables that you could select or make it tunable are the cell technology. You have three possible selections, so perovskite cells, CGIS cells, and thin film 3 junction cells. Then the ground station location, Spain, Germany, or Sweden, and then transmission frequency, 2.45 gigahertz and 5.8 gigahertz. So at the end, if you select one for every one of these three design parameters, you have one of 18 unique variant combinations, but or you can make it tunable so that the tool has to run the simulations with every one of the possible choices of these design variables. So at the end, as you can see in the right part of the slide, you obtain a table with all the simulations that you have run in the low fidelity. In this case, you have 6 simulations with the different inputs that you have selected. For example, the frequency or the cell efficiency, which is related to the cell technology you have selected, or the latitude of the ground power station, which is related to the location of the ground station, and a combination of the three main areas for every run. So every one of these combination is optimized for the related inputs. So you select one of that and you export to the architecture metadata. So you save the solution you like most, and then you pass to the high fidelity analysis. So in this case, the objective was to start from the design that you had done with the low fidelity and do some power simulations in different mission scenarios. Indeed, three of the design choices that you can make with the interface in this case are the simulation day, so our nominal day, or a worst case day for the eclipse. And the eclipse inclination, if you want to include the worst case for the eclipse inclination with respect to sun incidence to solar panels, and the SPS alignment. So if you want to comprehend what are the logic of alignment of the satellite during a day. So if you want to simulate a bad alignment of the spacecraft, what it happens during the simulations. Another parameter which had more impacts on the mass and cost estimation was the DCRF technology selection. So there were three options. So the solid state power amplifiers, TVTA, two-way tube amplifiers, and then klystron. So at the end, also in this case, if you select all the parameters, at the end you have one of 24 unique variant combinations. But also in this case, you could make it tunable so that the tools have to run all the possible cases. At the end, what you obtain in this case is also a table where, for example, in this slide, as is showed, in this case, we have run two simulations, one for the nominal day and the other was for the worst case of the eclipse. So what you see in the results is that the mass and the cost and the number of launches is not changing in this case because the CRF technology selected, obviously the design of the architecture is the same. What is changing is the power in the different part of the architecture. So obviously if you have an eclipse during a day, you will have less power during certain amount of times, and this will be compensated on ground by supercapacitor, as we will say in a later graph that I showed. Okay, so summarizing the workflow of the analysis, the idea was, as already Mark said, starting from this platform simulation environment where we put all the Simulink's blocks in the platform architecture in order to can have both data, architecture metadata, starting from the low fidelity analysis, which was a MATLAB code, and then also some Simulink models in order to simulate from an high fidelity point of view the power doing a different scenario that you could select from the interface from the UI. In particular, in this slide, I would like to show you a video of the demo of the code and of the interface. So if you can start the video. Okay, so you see then I'm changing in the low fidelity analysis the weight factor of the optimization, and I'm selecting the three different parameters. Then I make it tunable in making in the list. So I run the simulation. Now, obviously, the simulations are sped up. At the end, you obtain this table. You select the one you want, and as already said, you export to the architecture. So now there is all the inputs saved in the architecture metadata, and you pass to the high fidelity. Also in this case, you can change all the parameters you want. You can make it tunable. For example, in this first simulation, I make the day as tunable. So I obtain these different curves of power for the two scenarios, while the mass and the launch are the same. If I come back, I can change for the same architecture. I can run three different simulations with DCRF technology, different DCRF technology. So in this case, what is changing is the mass, the cost, or other parameters which were very important also to ESA to understand if this type of architecture is comparable with other energy sources, like, for example, levelized cost of energy, LCOE, or energy return on energy investment, or energy payback time. These were all parameters very important from an economical point of view, but that were all related to the technical point of view. This was one of the main things that we obtained thanks to this interface. Going to the next slide, in particular, I want to show you some outputs of these different analysis. These are two graphs that you can obtain by the low fidelity analysis. So on the left, you have a scatter plot of the results obtained with the different combination of parameters. So you have on the x-axis, on the y-axis, the cell efficiency and the transmission frequency, which were dependent on the input you selected, and you obtain the scatter of the solution obtained during the simulation for the three areas with respect to that. On the right side, instead, you have a graph where you can see the multiplicity of the combination of the three main areas, because it could happen that during the simulations there were multiple runs where they obtained the same solution also for different input parameters. So this graph permit to see what are the most recurrent combination of optimized three main areas. So this could be favorable to be selected and then to go to the high fidelity analysis with that design. Instead, in this slide, what I'm showing you are some outputs of the high fidelity analysis. On the left, we are talking about sensitivity analysis. That was one of the main objectives also of the mass and cost estimation. So for example, you could make a sensitivity on technical parameters, like in this case, the launcher fairing fill factor, and see what are the impacts on economic and energy parameters. So the levelized cost of energy and the energy return on energy investment. So you can see what is what the percentage of the fill factor, then you can have for that number the levelized cost of energy and the energy return on energy investment. On the right side, instead, you can see one of the outputs of the power simulation. So you have a graph where you have all the day simulated. In this case, I'm showing you a case of the worst case eclipse day. So you see that for all the curves, so for all part of the architecture, there is a null of power generation at one moment. So when you have eclipse on orbit, instead, the only curve that is continuous is the green one, which is the grid. So you have to assure that this 1 gigawatt of power that we have on baseload on ground have to be assured also when you have eclipse. And this is done by supercapacitors that we have on ground and that we have simulated also in our model to simulate this logic. Okay, so I pass my word to Serena again for the conclusion of the work.
Okay, thanks a lot. So the outcomes from Thales Alenia Space is that thanks to this work, we were able to have a more complete understanding about the mission from static and dynamic viewpoint, and also the capability to simulate these complex scenarios, as Lorenzo just explained to you, with different condition, variation, technology applied, and all the parameters that can be tunable into this tool. We were able to provide a complex data model through digital models, so to avoid also a huge amount of paper to explain data coming from different tool or different database. We are able more and more to centralize all this data in less models. We improved the efficiency, not just on tool perspective, but also on mission perspective, as Marco and Lorenzo have just explained, with the mitigation of risk analysis, because of course with this approach we were able to identify the critical aspects before. We are able much more to have an iterative design through this capability to merge different version of the model. And so as soon as we have a new version, we can immediately update into the system design and run the simulation without touching the simulation tool. And with this approach, we could be able to provide to the customer the cost analysis, even in a pre-phase A study. And we had improved also the communication, because especially in the first phase in which I design in Capella the model, I was constantly in contact with all the architects, and all the architects were participant and contribute to this phase. And offshore, for sure, we are increasing this capability to pass from the static environment of Capella towards the dynamic world of Mathworks. I leave the floor to Mathworks also to give their viewpoint on this project.
Thank you, Serena. Well, first of all, it was a very good project and nice for us to work on it. And so what we did, we took kind of the occasion to make this framework. And the framework is both the bridge and the analysis expandable. That's why, for example, when I was talking about the customization, we choose not to hard code any of this rule into the translation script, but externalize this to a JSON configuration file so it could change if and when needed. For next phase of this project or another type of mission. The analysis framework is also kind of flexible because essentially what it does is looking at some specific metadata and run simulation on a model that you are telling to do it. So you could configure the UI to work on another system of system. It doesn't need to be this one specifically. What for us was very good to demonstrate is that actually it's good to have this cross-tool interoperability. So there is a chance to use the right tool for the right job at the proper time, and there is like not the necessity to say, oh, one tool fits all. We could use different tools for the different needs that the project will have at the different time of the life cycle, and leverage the best out of the two. One thing that I wanted to say is that this bridge is there is a bridge, or there used to be a bridge between Capella and Simulink. This is something else. The bridge is with System Composer, which would allow you to import more things from your Capella model, including, for example, profile, as this concept do not exist in Simulink, but they only exist in a System Composer. So that's one of the aim of that we also wanted to get out of this project.
Yes, thanks, Joel. What are the pros and cons of Solaris compared to a ground solar station?
So the main pros of space-based solar power with respect to a ground station is that solar power on ground is very weather dependent. So mainly, for example, you cannot have power generated by a solar ground station when it is night. And also, as I was already saying, is very weather dependent. So if you have a rainy day, you cannot generate power, you can have interruptions, and also you have problem in placing this infrastructure on grounds in different countries. The pro in this case for the space-based solar power is you can have 24/7 baseload power generated by our infrastructure. So also when it is night, or it is a bad day on Earth. The cons, of course, is that we are talking about very big, I would say enormous architectures that you have to build in space, because we are talking about kilometers squared of area of ground power station on ground, but also solar panels on space. So it is very complicated to assemble it, to control it, and to launch it from a cost point of view.
Okay, thanks for that. How complicated is the transfer from the Capella model to System Composer? Is there a lot of manual work required?
Let me start with say it depends. So if you depends what you want to transfer. So and depending on that, you need to create this JSON file, which creates the mapping between elements that you want to look in Capella and convert into System Composer. So the manual work that is necessary is, for the first time import, compile this JSON file. And obviously, if you do decide to, let's say, for example, you only want to import the logical part of the Capella model and you don't care about the functional one, so you compile the JSON file to give the translation rule. That's one-time effort. If you later on you change your mind, then you say, okay, I also want to import the functional part, or I want to import the requirement, something else, you need to update. So the manual work, which I guess is not a lot, as soon as you have a stable configuration file, it's where it is there. Else everything is handled by the bridge.
Okay. Well, I was sure that someone will ask this question, but is your bridge will be available for free or not?
So thanks for the question. We all bet that this was going to be asked, you right? So at the moment it's not available, and you need to ask us for the bridge. So we are not asking for money for this for the time being, but it's not downloadable from anywhere. For clarity, if you look in on the web, you would find something called SysML connector to translate SysML model to System Composer. That is not what we show you today. So if you're interested, please reach out, and then we can talk how we can get the connector in your hands. There are plans to make it publicly, but we don't have yet a date or a stable kind of a time frame that I can give you.
Well, maybe on my side, I'm curious to know more about maybe the complexity of the model you had to handle with. Do you have any figures to share regarding the number of I don't know, attributes or elements you have to manage?
On the logical architecture, as we say, as it was a pre-phase A study, it wasn't a model like a phase C project, so we don't have this maturity. So in terms of function and component, we are around, I don't know, around 30 more or less component between what is in space, in orbit, and on ground, because Thales was responsible of both the orbit architecture and the ground architecture. So it wasn't so big as other model that we are doing for phase B or phase C deliverable. So yes, I would say around 30, maximum 50 elements, more or less, and I don't know about an interconnection, but it should be on the same order of magnitude. Yeah.
Okay. How many people work on the model, but how many people work on each model? Maybe might be interesting.
I work on the Capella model. I was the only one helped by the architect. It's an approach that we applied often in Thales because we saw that one model close to the architect is a more efficient way to deliver in a very strict time, because we have maximum 2 or 3 months to deliver the model. So right now we don't have the time to form to train all the architects on this model. And Lorenzo and Marco were the ones who were working on the system composer. So we were 3, but it was a project with in total maximum 10 or 15 people. So I would say 30% were working on the model.